So in week number 9, we're going to be talking about hypothesis testing. So we're essentially going to explain the process used in hypothesis testing. So it's all about hypothesis testing. We're going to state the null and alternative hypothesis. We're going to calculate this critical value for the Z test. And we're going to do it in steps. So there's 5 steps used in hypothesis testing. So we're just going to understand 1, 2, 3, 4, 5. And then we're going to construct a hypothesis test on a mean when basically a sigma is known in this particular case. So what is hypothesis testing? So researchers are interested in answering many types of questions. So these questions are stated as claims about a population, and the decision-making process for evaluating these claims is called hypothesis testing. So researchers define the population under study, state the hypothesis or claim to be investigated, set the significance level. So this is remember, this is our alpha, and it's related to our confidence level. Select a sample from, and it's related like 1 minus that probability. Select a sample from the population, collect the data, run the statistical tests, and research a conclusion. So there's 3 possible methods for performing hypothesis testing. Essentially, there's the traditional method, which we'll talk about, p-value method, which we'll briefly talk about, and confidence interval method, which is actually in your sample problems if you go through that one. They're all basically the same thing. So we're going to stress more the traditional method, and we're also going to mention the p-value method, and this is again in your exercises. So a statistical hypothesis is just a conjecture about a population parameter. The conjecture may or may not be true. So we don't know if this is true. It's just a hypothesis. There are always 2 sides of a conjecture, the conjecture and its complement. So hypothesis about a population parameter. So suppose you have a pharmaceutical company, and it's concerned about the mean potency mu of an antibiotic. Does it meet the minimum government potency standards? You can almost think of this as you have 2 possibilities. The mean potency mu does not exceed the mean allowable potency, or the mean potency mu exceeds the mean allowable potency. So this is just basically an example, a test of hypothesis. You can think of it as, the vaccine. Did it meet the allowable criteria for, for safety standards or etc. So we can think of it and relate it to things that are happening in the real world. A very classical example of how to relate this is in a courtroom trial. Is very similar. So in a courtroom, a person is tried for a crime. So I think Law and Order, right? The jury needs to decide one of 2 possibilities. Is the person So the person is either guilty or innocent. So we have to decide when doing a test of hypothesis in this particular situation. Think of yourself as the jury. Are they guilty or innocent? So we assume always that the person is innocent. So we make that assumption that the person is innocent. And then the prosecutor presents evidence trying to convince the jury to reject the original assumption of innocence and conclude that the person is guilty. So the prosecutor is trying to provide evidence and prove that, or with a sufficient, it's not proof, but like show enough evidence that beyond a reasonable doubt that this person is guilty. But you make that assumption, that hypothesis, and initially that the person is innocent, and then you're trying to show the opposite, that they're actually guilty, the prosecutor. So the statistical test for our hypothesis, there's 5 parts. So the first part is the null hypothesis. So this part is assumed to be true until we can prove otherwise. So you assume this is true. And so this is assumed to be true. The statistical hypothesis that states that there is no difference between a parameter and a specified value, or that there is no differences between 2 parameters. This is the null hypothesis. Now, the alternative hypothesis, lowercase here is A, up in the null, it was like a not here, or a 0, whatever. So the alternative will be accepted as true if we can disprove H naught, the null hypothesis. So statistical hypothesis that states the existence of a difference between a parameter and a specific value, or states that there is a difference between 2 parameters. So that is the first step, or the first 2 steps, is set up the null and alternative hypothesis. Okay. So the null hypothesis always states that the parameter is equal to a specific value or to another parameter. The alternative indicates change. So the alternative hypothesis claims that the parameter is either it's not equal to, greater than, or less than a specific value or another parameter. So it's not equal to, so, you know, it could be greater than, less than, whatever. You get the idea. So the null hypothesis is always, so this is the alternative. And the null hypothesis is always equal to. So it's stated using that equal sign. So the skeptic will not reject the null hypothesis. So you do not reject the null hypothesis unless the evidence in favor of the alternative hypothesis is so strong that she rejects the null hypothesis in favor of the alternative. So you're looking for essentially enough evidence for the alternative hypothesis that you say no to the like the null hypothesis. So you're looking for evidence here. It's almost like a, oh yeah, back to the examples. So in the pharmaceutical case, the null hypothesis would be does not exceed allowed amount, and the alternative would be the mean here exceeds the allowed amount. In a courtroom trial, I always like to think of, relate this to something straightforward. The null hypothesis is innocence. The alternative would be guilty. So beyond a reasonable doubt, you're looking for enough evidence that you would convict the person on trial, but you assume innocence. Now, if you fail to reject the null hypothesis, you typically accept the, we typically do not accept the null hypothesis as true. So in this particular case, you say, you don't say the person is innocent, technically, you say like not guilty. So in court, you say guilty or not guilty. The jury decides, it makes that distinction. So state the null and alternative hypotheses for like these examples. So the average age of first-year medical students, So the average age, I like to just read it twice, is less than 29 years. So we're mu here. So we know the null is where it's equal to. And the alternative is what we are looking for evidence. So the alternative would be the average age is less than 29 years. Now, this is a left tail, because if you draw like a little picture, let's say, we're looking for this value where it's less than 29. So this is a left tail test, which is what's written here. Okay, so the second one, the average number of seasons in which an NBA player participates is 4.71. Okay, so we're thinking, so the null is where the average is 4.71. Sorry, 2 dots there. So versus the alternative, where the average age is not equal to 4.71. Okay. So if it's not equal to, let's say like this is 4.71 is the average. So we want to see if it's really not equal. So like these parts over here. So this would be two-tail tests. So let's just see. So the average number of monthly sessions on the internet by a person at home has increased from 36. So the null, again, is that the average is 36 versus the alternative that the average is greater than 36. Now, of course, we can just draw this. 36. It's this portion over here, so it's right-tailed. So D, I'll write D over here. The average cost of a basic cell plan is at least $79.95. So the null is, of course, equal to $79.95 versus the alternative. Cell phone plan is at least, so at least, but not more than. So it's just about watching the words, so like at least or more than, look for keywords. And then you can draw this. So this would be like, let's say here. This is less than. It's a left tail. And then the last one is the average weight loss for a sample of people who exercise 30 minutes per day for 6 weeks is 8.2 pounds. So let's say for E, the null here is, let's say, 8.2 versus that alternative. So is that it's different. So it's not 8.2. And then we can just quickly like draw like a little sketch. So This is 8.2. We want to know if it's different out here. And this is two tails, because there's two tails here. So once we kind of set up our null and alternative hypothesis, and it's just about reading the question correctly, we can calculate this test statistic and its p-value. Like you could do it either this way or this way, whichever way you want. So I'll first go through the first classical method in a lot of detail. And then I'll go through the p-value method a little bit quicker, and then confidence again in the exercises if you are interested. So a single statistic calculated from the sample that will allow us to reject or not reject this null hypothesis. That is the first method of doing things. The second method, and/or, because they all are just basically the same thing, is a probability calculated from the test statistic that whether the test statistic is likely or unlikely, assuming the null hypothesis is true. That's the second way. That's the p-value. And the third way is, so that's why I say and/or, is a region or confidence interval calculated from the test statistic that measures whether this test statistic is likely or unlikely, assuming the null hypothesis is true. That's the third way. So then, and they're all kind of like the same way, like 1 and 2 is very popular because like there's printouts that, you know, the computer will just give you the p-value. So it's important to be able to understand, go from the classical method, understand the theory to the p-value. Anyways, the numerical value obtained from a statistical test is called the test value, or this test statistic, which I'll show you what that is. And then the last steps. So the critical or rejection value has to be obtained. So this is a rule that tells us for which values of the test statistic or for which p-values this null hypothesis should be rejected. And this really depends essentially on our alpha, our what level of significance do we wish. And then we make a conclusion. Obviously, we reject the null hypothesis, or you do not reject the null hypothesis. So you think of that again, the person is guilty or not guilty, you know, so you make that therefore statement essentially about the reliability of your conclusion. So there's types of errors that can be introduced here. So this is when the null is true. Let's look at the correct decision. So if the null is false, so let's say, so whatever the hypothesis is, the null hypothesis is false, and you reject the null hypothesis, then that's okay, right? Suppose the null hypothesis is true and you do not reject the null hypothesis, then you made a correct decision. But then there's cases of, well, what happens if the null hypothesis is true and we decide to reject the null hypothesis? So that is an error. So that's incorrect, right? Like you don't want that situation. And that's called a type 1 error. And that really depends on alpha. So alpha depends on this type 1 error. And this is the evidence. Like this is, let's say we want a 90% confidence interval, or we want 95% or 99%. That really depends on this alpha. Now, which I'll show you, if the null hypothesis is false, and we do not reject the null hypothesis, this is also incorrect. So like these are incorrect. This is called a type 2 error, and this is a beta error. And this is harder to actually account for. So So let's look at the jury example to make it a little bit more clear. So let's relate it to something that we probably have seen before on television or watching movies. So the null is, let's say, true. Like, let's say there's a person and they're innocent, and we reject, okay, let's say here, let's start with the correct decision. So let's say the null hypothesis is false. They're not innocent. But we suppose the null hypothesis is false. So they're not innocent, they're actually guilty, or like they're guilty. And we reject the null hypothesis of innocence. And so we convict the person, so they go to jail, right? So in this case, they go to jail, so it's all good. So justice is served in this situation. What about over here? If they are innocent, so the null hypothesis is innocent, and we do not reject the null hypothesis, so that means they get out because they're innocent, so they get to leave jail, right? Or they leave the court system, they're acquitted, essentially. Okay, so that means like they, I don't know, celebrate because like they won the trial, essentially. So they're winners and they get to leave and go home. So go home. What if the person is innocent, but we fail to reject that null hypothesis? They're actually convicted here in this particular case. Okay, so this means like there's basically justice was not served because which isn't good. I shouldn't put an X here. So no justice, like, so this is an innocent person going to jail. So in this case, an innocent person goes to jail. Right? If you ever watched some movies like The Shawshank Redemption on Netflix or anything, like you can see how this isn't a good situation to be in. Now, this really, again, depends on your evidence, which is related to your alpha. So maybe this means you have to increase this alpha so innocent people don't go to jail. So, and this has happened in the court system. You do see it where, unfortunately, innocent people are convicted. They do go to jail because maybe, they were convicted on circumstantial evidence, and the circumstantial evidence is not really, it shouldn't have been enough to convict the person, but it did convict the person. And now there's this last case, of course, where the person is not innocent, but we fail to reject or acquit this person. So this isn't obviously good either. This is that beta error. There's not really much we can do in this particular situation if we just did not have like that evidence. So that's the types of errors. So there's the levels of significance symbolized. So like these levels of significance are symbolized by this alpha, and it's the maximum acceptable probability of making a type 1 error. So the probability of this type 1 error is alpha, actually. So we want to keep the probabilities of errors as small as possible. So the value of alpha is the significance level, and it's controlled by the experimenter. the value of beta is difficult, if not impossible, to actually calculate. So rather than accepting a null is true, so you don't really accept the person is innocent, you just say, without being able to provide a measure of goodness, we choose to not reject the null hypothesis. So there's just not enough evidence to say that they're guilty or whatnot. So this is what I alluded to earlier in the example. So like the null hypothesis is true. It is true. The value of X bar should be close to mu. So whatever that statistic, it should be close to this value mu. And Z will be close to 0. Remember, if this is on the Z, if we convert the raw data X to Z, etc. If the null hypothesis is false, X bar will be much larger or smaller than mu naught, and Z will be much larger or smaller than 0, indicating we should reject. So this is a figure of two tails. So this is the rejection region. And this is also the rejection region. And this is the we accept here, the null. And we reject the null on this side, and we reject the null on this side. So we can create kind of like, so I'll mention confidence intervals quickly. Like you create a confidence interval this way, or you can see where the test statistic falls. Does it fall in here or in here, or does it fall in here? And if so, then we can accept the null. So one-tailed test, so that was a two-tailed test. There's two tails. Sometimes we're interested in detecting a specific directional difference in the value of mu. So alternative hypothesis to be tested is one-tailed. So the alternative can be greater than or less than, like you see here. So the rejection regions and p-values are calculated using only one tail of the sampling distribution. So again, this depends on the wording of the question. So the rejection regions and p-values are calculated using only one tail of the sampling. So the alternative here, this would be one tail, where, like, let's say it's mu is greater than, let's say, a number. So it'll be on this side. So this is, again, our rejection region. This is also a rejection region. This is our accept. And then over here, we accept. So we create like these regions for the one-tailed test. Now, once you've calculated the observed value of the test statistic, we calculate its p-value. So the p-value, you don't have to calculate technically the p-value. You just could conclude things, which I'll show you. So the p-value is the probability of observing, just by chance, a test statistic as extreme or even more extreme than what we've actually observed. If the null hypothesis is rejected, this is actually the probability that we have made an incorrect decision. So let me just, so if the probability is very small, less than some pre-assigned significance level alpha, so if it's very, very small, the null hypothesis can be rejected. So if it's a very, very small value, less than alpha, then we can reject this null null, because this is less than this. So the p-value, by definition, is probability you made an incorrect decision. so let's continue. So to make our decision clear, we choose a significance level. So we choose that evidence or that reasonable doubt. And we say, like, let's say alpha is 0.01 or 0.05. Remember, like, this is like basically 99% confident, or this is a 95% confidence level or interval, whatever you want to say. And alpha is the complement. So to find the critical value, the researcher must choose a significance level, called this alpha. This is what I just said. So remember the complement of the confidence level. So it is, let's say 99% will be 0.99, which is 1 minus this. So this would be our alpha, would be 0.01. So if this p value is less than alpha, then the null hypothesis is rejected as false. So we reject that null hypothesis. And you report that your results are statistically significant at this level, whatever that level is. If the p-value is greater than alpha, the null hypothesis is not rejected. And you report that the results are not significant at alpha. So let's just summarize this. So if alpha equals, like, let's say 0.01, it could be whatever you choose. What would be the critical value that marks this dividing line? So this is called, the dividing line is called like this critical value between not rejecting and rejecting. Anyways, if this p-value is less than or equal to this alpha, then it is rejected. The null hypothesis is rejected. So we reject that null hypothesis in favor of that alternative hypothesis, because the evidence here is so small, or the evidence here is, let's go back. Where did it go? So it's rejected as false. So it's a very small value. So there's not enough evidence for the null hypothesis. So this is why it's rejected. If the p-value is greater than alpha, this null hypothesis is not rejected. It'll be easier once I show pictures. So the dividing line occurs when p value equals to alpha, and this is called this critical value of the test statistic. Remember, like, this is your like 1 minus alpha, and then you have your alpha divided by 2 and alpha divided by 2 if this is a two-tailed test. So we can calculate this dividing rejection region here and here, depending on what your alpha is. So it'll be alpha divided by 2, and look up like these Z's in the table to find like these rejection regions at this particular alpha. So steps for finding the critical values for specific alpha values. So the first step is draw the figure. Always draw a picture. This is basically that normal curve, and indicate the appropriate area. So if the test is left-tailed, the critical region with an area equal to alpha will be on the left side of the mean. So that's what I earlier drew. So it'll be just on this side. If the test is right-tailed, the critical region with an area equal to alpha will be on the right side. These are all normal curves. If the test is two-tailed, alpha must be divided by 2, and 1/2 of the area will be on the right, and 1/2 will be on the left. So area here and over here. But again, it says 1/2 of the area will be to the right of the mean and 1/2 will be to, or the left, sorry. So for a left-tailed test, use the Z value that corresponds to the area equivalent to alpha in the table. For a right-tailed test, use Z value that corresponds to the area to 1 minus alpha, the complement of alpha in that table. So it's because of the table of how the table is either it's drawn on one side. So for a two-tailed test, use the Z value that corresponds to alpha divided by 2 for the left value. And this will be negative, of course. Like this side is, of course, negative. And negatives over here. And for the right value, use the Z value that corresponds to the area equivalent to 1 minus alpha divided by 2. Or use the opposite of the left value due to the symmetry. Because it's symmetric, it's just going to be, if this is like, let's say, negative Z alpha divided by 2, symmetry is, obviously, it's going to be the same thing. And of course, this is going to be positive, which we found out before in previous weeks. So statistical decisions are not actually proofs. Statisticians only state that there is or is not evidence to conclude that a claim is probably true or false. Nothing is actually proven. The only way to prove something would be to use the entire population. It's usually impossible or impractical to do this, especially when the population is large. So like, again, like these are just not proofs. Like it's the same with the vaccine. It's not technically like a proof when they were doing like small trials. You have to use a huge trial, randomized experiment, all this. So you have to randomize the population. Only like a randomized experiment can actually prove anything. Anyways, a Z test for the mean, section 9.2. So that was like a little bit of background, but it's easier once we actually see some applications to this. But we still have to go through some theory. So a large sample test about a population mean. So take a random sample of size like n being greater than or equal to 30 from a population with this mean and standard deviation. So we assume that either sigma is known, so that standard deviation is known. We're going to talk about later on what happens when it's unknown after the next lecture component, or that S is approximately equal to sigma since n is very large. So we have to make these assumptions again that n is greater than or equal to 30, sigma is known, and this is large. The hypothesis to be tested is, so there's versions. We have our null hypothesis with the equal sign versus our alternative that it's either different, it's greater than or less than, etc. Some mu naught. So that's just like a number for what we're testing. So we can calculate this test value. So this test value, our test statistic, is just that observed value minus the expected value divided by the standard error. So thus this Z test, or this test statistic, is a statistical test for the mean of a population. It's important when the sample, it is a random sample, either that n again is greater than or equal to 30, or the population is normally distributed. So it can be, as long as it's normally distribution, that's okay too. And that sigma is known. Again, sigma has to be known in this case. So Z, like we did before, is just x bar minus mu divided by sigma divided by square root of n, and we can approximate this if sigma and s do approximate, and we get this value. So since X bar has an approximate normal distribution, this mean and the standard deviation, using that central limit theorem. Remember, this is due to that central limit theorem. So recall like the steps. So state the null and alternative hypothesis and identify the claim, find the critical values. So the rejection regions, etc., for alpha. So it depends on if it's one test, two tests, etc. Compute the test statistic and its p-values if you wish. Sometimes a computer can give you these p-values also. Make the decision, reject or not to reject the null hypothesis, and summarize the results. So the statistical significance. So what does it really mean? So if the p-value is less than 0.01, we reject the null hypothesis because there's evidence in favor of the alternative and the results are highly significant. So that is great when they're highly significant. If the p-value is between 0.01 and 0. So this means like you're 99% sure, basically. If the p-value is between, like, let's say 95% and 99%, sorry for my scribbling, we reject the null in favor of the alternative, and the results are statistically significant at that point. So that is also a great point. And it's sort of like we think of the vaccine, like when I remember when they were coming out and like, oh, like this vaccine is like 95% preventing the virus, or 94%. I was thinking, oh, like they were really trying to get it to a significant statistical level in order to release this to the population, because 95 is typically like the standard of what we see this in research. We want things to be at like this 95% level, even though it's what kind of choose this is in the literature. So if the p-value is between like 90 to 95%, you do not actually reject the null hypothesis, but the results are tending towards significance. So that's still okay, but it's not as, of course, great as over the 95% level is where you could typically say confidently and publish research, even though, anyways. So consider, and then we consider the consequences of, in this particular case, of type 1 errors before rejecting the null hypothesis. So we think like, are there errors? Do we have to check things? And anyways, if the p-value is greater than 0.10, we do not reject the null, and the results are not statistically significant. So let's look at examples instead of me talking so much about theory. So let's say we have a mayor of a small city claims that the average income in his city is 35K with a standard deviation. So this is our standard deviation of 5,000. So this is the claim. We take a sample of 64 families, so that is our N, and find that the average income is actually 30K. Is this claim correct? So what is the null hypothesis? What is the alternative hypothesis? Anyone? Okay, so we test that the mayor is correct. So we assume that the mayor is correct, and that is the null hypothesis of 35. Let's go back. And we have like this average and we test it. So this is our X bar, that average. So the alternative is the mayor is wrong, that it's not 35K, the average. So we start to assume that the mayor is correct and we test that mu is 35K. So the best estimate of this population mean is the sample mean of 30K. So from the central limit theorem, the sample mean has okay, we'll take a little bit of a break. So we know from like that central limit theorem that the sample mean has an approximately normal distribution with like this mu is 35K, and the standard error is going to just be the standard error is sigma divided by the square root of n. And remember, sigma in the question was 5,000 and the square root of n was 64. So this is where we get 625. Now, the sample mean, 30K, we can calculate our Z is our X bar minus our mu divided by our standard error. And so we calculate that Z value and we get -8. Ooh. So we know that -8, so Z is, that's the amount of standard deviations it is away from the mean. -8 is very far away from that mean, that center point. So the probability of observing a sample mean this far away from 35 is nearly 0. So it's very far, assuming that this null hypothesis is actually true. The probability is near, this is a very, 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 very rare event. So therefore, from the empirical rule, values more than 3 standard deviations away from the mean are considered extremely unlikely. So such a value would be extremely unlikely to occur if the null is indeed actually true. So this would give reason to reject the null. So since the observed value, 30K, is so unlikely, we choose to reject this null hypothesis that the mayor was correct and conclude that the mayor's claim is incorrect. So the probability that we have observed such a small sample mean just by chance, when in reality, this probability that the mean is 35K is nearly 0. So this is just an idea, an example of how to do this. Now, let's add some evidence into things a little bit and make it more set of criteria. In this previous example, the numbers worked out because -8 is just so far away that, you know, it's probably not true. So first example here is, let's say a researcher believes that the mean age of medical doctors in a large hospital system is older than the average age of doctors in Canada, which is 46. Assume the population standard deviation is 44.2. So we can just write things out to the side. And a random sample of n 30 doctors, so n equals 30, from the system is selected. The mean age of the sample is 48.6. So we want to test this. So test this claim at the alpha is equal to 0.05. So we set up the null hypothesis. So and then you reread it again. So a researcher believes that the mean age of medical is older than. So that we want to test that this mean is, the alternative is greater than, so the mean is greater than 46, average age. So versus the null that the mean is equal to 46. So we test that Z. So remember, Z is equal to, at this point, we know this, it's X bar minus mu divided by sigma divided by square root of N. Okay, from previously. So we calculate that Z, that test statistic, we get 3.39. Okay, now, is this left tail, right tailed test? Well, we draw like a little picture. And it's going to be, because it's right tailed, it's greater than, so it's on this side somewhere, is the idea of, and our null here is 46. And our Z is 3.39. That's our test statistic with this data. Now the alpha is 0.05. So we have to like look this up in the table. Let me pause. So because alpha is equal to 0.05, you know, this part is like going to be 5%. And this is going to be 95%. So now we can like look this up in the table at this particular evidence claim. And at, let's say, alpha at 95%, that Z value is 1.6, you could say 45 or 1.65. It's either between here and here. Like those particular values. So we could say 1.645 or 1.65. So this is the cutoff region, like let's say. So this is the region here where Z is equal to 1.65. Okay, that's the critical region. So we're going to reject everything over there. Let's use colors. So we're going to reject, this is a rejection region. Reject the null hypothesis from here to here. Now, we see that this test statistic with this data, we computed it and it's actually right. It's, let's say here, it's at 3.39. So it falls in the rejection region because it's, if you draw like a little picture, it is greater than 1.65. It falls in that rejection region. So therefore, we make this decision is to reject the null hypothesis because it falls in the rejection region. So there is enough evidence to support the claim that the average age of doctors in the system is greater than the national average, because this value falls in that area of, with this particular significance of alpha being 0.05, which corresponds to 95% certainty. Now for this question, so for a specific year, the average score on the SAT math test was 515. This variable is normally distributed. So the math test was 515. This is normally distributed and the population standard deviation is 100. Okay, I like to just underline keywords. A school superintendent wishes to see if her students score significantly below the national average on the test. So were they less than? She randomly selects 36 students, student scores as shown. So you have this data. At alpha equals to 0.10, is there enough evidence to support the claim? So is there enough evidence? So the alternative is that it's less than, because again, want to see if it's below the national average. So that's the alternative, that mu is less than 515 versus the null hypothesis that mu equals 515. Now, we could compute the average x bar of all these numbers. You could put this in an Excel file if you wish, and you get what x bar. So if you see all this data, and you start counting first, 1, 2, 3, 4, 5. So 6 rows and 1, 2, 3, 4, 5, 6. 6 columns. So there's 36. So just first check that and set up the question for yourself and make it a little bit easier. So you find x bar, then you calculate that z statistic. So remember, z is equal to our x bar minus our mu divided by sigma divided by square root of n. This is again because of that central limit theorem. And so alpha is equal to 0.10. We can draw a picture first. And we are testing to see if it's less than 515. So because it's one-tailed left test, it's on this side. So it's a left-tailed test. We can look this up in the table. Okay, because of symmetry, like we see like this picture, this is left tail and to like this particular area. The normal curve is the other way. So we could, so just like look up the probability of 0.10 in the table due to symmetry, because we just want like this little part here. As you see in this table, actually, so we just want like this little part here in the table. It's not due to symmetry. It gives us the value exactly, this z. So we can look it up. And so we see what is the value closest to 0.10, which is, I think, this value. So it's negative 1.28 is our z. So z here is, the z's value is equal to negative 1.28. So that is the evidence, and that is the region of where we calculate this. But we notice our test statistic is negative 0.36. So it would be like, let's say over here, I don't know, somewhere, or maybe close. This is the raw data. This is if it's centered at 0. So for the z, so this is negative 0.36. So once we get that data, you see like, well, does this fall in the rejection region? No, right? Like this is where we reject it. This is where we accept it. So this value that we just calculated, this with this test statistic, falls in the accepted region, not the rejection region. Therefore, the decision is to not reject the null hypothesis. So there's not enough evidence to support the claim that students scored below the national average. So no. Here is another example. So the average cost of rehab for stroke victims is $24,672. To see if the average cost of rehab is different, so keyword here is different at a particular hospital, a researcher selects at random a sample of 35 stroke victims at the hospital. A researcher selects at random 35 stroke survivors and finds the cost is $26,343. The standard deviation of the population is here given, and at alpha it's equal to 0.01. Can it be concluded that the average cost of rehab is different than 24,672? So right off the bat, we know the key word here is different. There's no greater than, less than. So it's going to be a two-tailed test. So the alternative, we're testing the alternative that it's different than 24,672. But we assume that the null hypothesis is true, that the mean is equal to 24,672. Now we calculate, of course, that Z, which is equal to, of course, our X bar minus our mu divided by our formula here that we need to know. And we just like plug in our numbers. We have our X bar, the average cost of rehab in stroke victims is this. So we have our X bar, our standard deviation is here, etc. Okay, and we have 35 here. And we could all, of course, write it out. We could draw like a little sketch just so so this is our H naught. In terms of the Z, if we transform it, that will be 0. We want to see it, or in the X data, it's 24,672. And we want to calculate this out here. Now it's a two-tailed test. So we'll look this up for like this alpha of being 0.01. So this means like this is the 99%. This would be like 0.5%. And this would be like 0.5% over on this side. And you can see like they would add up to 1. So we can like look this up essentially in the table. And 0.0. And we can just like choose, I guess, like this value here. Sometimes you could go in between, but let's say negative, if you had more digits, like in the table, I think it's this value. This is only 1, 2, 3, 4. We have 5 digits. It's this one. So it's negative 2.58 is the closest value. And then due to symmetry, it's going to be 2.58. So that's how we get our rejection regions. And remember previously, like there was a table, which I can show you. So previously, we used like this particular table for the levels of confidence and corresponding critical values. So you can just like use this table if you wish. Our alpha was 0.01, which corresponds to a 99% level of confidence, or 0.99, and the critical value is 2.58. So we can essentially use like this 2.58 and negative 2.58 here. And this is our critical value that we're going to check to see if this is in that rejection region. Well, we see that it is in the rejection region because 3.04 falls in the rejection region. So we therefore reject the null hypothesis since the test value falls in the critical region. So we reject. And so there's enough evidence. So what does this mean? So if we reject the null hypothesis, then there's enough evidence to support the claim that the average cost of rehab is different from 24,672. So we're in favor of that alternative hypothesis. So this is the same thing, more examples. But with p-values. So the daily, because I kind of didn't go into detail exactly of the p-value. So the daily yield for a chemical plant has an average of 880 metric tons for several years. The quantity control manager wants to know if this average has changed. So has it changed? Is it different, essentially? So we already know that from this, it's going to be two tails. She randomly selects 50 days and records an average yield of 871 metric tons. So this is what she records, our average, with the standard deviation of 21. So the null hypothesis is that it's the same. It's the mean is 880 versus that it has changed, that it's different, that this average is different from 880. We can calculate Z. Now it's a sample, so but it's n is greater than 30, so we can make this assumption that sigma is approximately equal to our S in this particular case. So we calculate X bar minus mu divided by S divided by square root of N, and we get negative 3.03. So that is our test statistic. Okay, now it doesn't really tell us the alpha here. So our p-value, let's compute this. Well, this is our p-value when our Z is greater than, because it's a two-tailed test, 3.03, and less than negative 3.03. So we can just look these up in the table. So we look it up, negative 3.03, which is right here in the table. And we get our values right here. And because it's symmetric, this p-value and this p-value, they're going to be the same. So we just can multiply it by 2, and we have our p-value. So this is very unlikely to occur, like very, very small probability that this test statistic actually happens, that it actually occurs. So it's about 2 times in 1,000, assuming that this is true. Very, very small. So to make our decision clear, we can choose the significance level, or the researcher can give this in the question. And we can say, like, let's say alpha is equal to 0.01. So if this p-value is less than alpha, so if it's less than alpha, this null hypothesis is rejected as false. And you report that the results are statistically significant at that level alpha. If the p-value is greater than alpha, the null is not rejected, and you report that the results are not significant at alpha. Since our example here, our p is very, very small, it's less than, so we reject the null hypothesis, and and conclude that the average yield has changed. And so I almost think of it as the reverse situation. It's like what is happening over here versus what's happening here. So it takes a little get used to. So that is how we do the p-value. So what is the critical value of z that cuts off exactly alpha divided by 2? So our alpha, we chose it to be 0.01. We divide by 2. So we can draw like these pictures. So if our alpha is 0.01, then we divide it by 2 and we have, it's going to be 0.005. We can like look this up in the table, which I think we just did, and it's negative 2.58 and 2.58. So those are our rejection regions. So for this example, we had our test statistic z is equal to negative 3.03. So that falls in that rejection region. So this null is rejected at the 1% significance level. So I'm just tying it back to the test statistic. So it's the same way. So you can do the p level of rejecting the null, or you can do the test statistic falling in the region. Let's see an example of a one-tailed test. So to find out whether Canadians are exceeding an average daily sodium intake of 3,300 milligrams, a sample of 100 Canadians is selected, and the mean and sample deviations of daily sodium intake are found to be 3,400 and 1,100, respectively. Use this alpha of equal to 0.05 to conduct this test of hypothesis. So rereading it, we see that here is our mean that we're testing, and we want to see, does it exceed our daily intake? Is it greater than this value? So so we assume our null is that it doesn't exceed. Okay, so it's first setting it up. Then we calculate that test statistic. So we found using data that the average here is here in our standard deviation or of our sample. Okay, and we calculate 0.91. Okay. So so let's do the critical value approach first. So that critical value of z that cuts off exactly alpha equal to 0.05 in that right distribution. Is we're looking for this way because we know it's right because of this. Okay. So we can look up this alpha here of 0.05 in the table. So because of the symmetry, and the value here is right. So it's 1 minus it. So we could just think of it as this portion. So it's going to be 1.65 or 1.645 because it's between like these two values. We find our z. So for our example here, our z is 0.91. So it obviously is not in our rejection region, and our null is not rejected. So there's not enough evidence to indicate that this mu is greater than. So this is what we did. So it's not rejected because it's accepted here up into this point, and then rejected in that area. Okay. What about the p-value approach? So this is the probability that our sample results or something even more unlikely would have occurred just by chance when this mu is equal to 3,300. So our p-value, we can calculate this using our table. So we can look this up. So because z is greater than 0.91, we want 1 minus that probability, which we just looked up in the table. So it's 0.1814. That is that probability that our sample, because it's computed from our sample data, results in something even more unlikely, very small. Okay, since the p-value is greater than our alpha, so it's greater than this, this null is not rejected. So because it's greater than, p-value here is greater than our alpha, therefore our null is not rejected. So there is insufficient evidence to indicate that this mu is greater than 3,300 milligrams. So our next example here is just 2 more examples. A researcher wishes to test the claim that the average cost of tuition and fees at a 4-year public college is greater than 5,700. She selects at random sample of 36 4-year public colleges and finds that the mean to be 5,950. The population deviation is 659. Okay, is there evidence to support the claim at this alpha equals 0.05? Let's use this p-value method to understand it. So we want to see, rereading the question again. Okay, so a researcher wishes to test the claim that the average cost is greater than, so there's the keyword, greater than 5,700. So we assume the null hypothesis is equal to 5,700 versus the alternative that it's greater than 5,700. We compute that test a statistic, which is 2.28, and we can compute this area under the curve at z equals 2.28. So at 2.28, it's right here. So that is our value. Then we want to, because it's of course right-tailed, we want to subtract 1 minus this value to get that that probability, that p-value, that 0.0113. So our p-value is less than our alpha. It's hard to see. Yeah, it's less than. So therefore, the decision is to reject the null hypothesis. So there is enough evidence to support the claim that the tuition is greater than 5,700. I think this is our last example. So a researcher claims that the average wind speed in a certain city is 8 miles per hour. A sample of 32 days has an average wind speed of 8.2 miles per hour. The standard deviation of the population is 0.6 miles per hour. And this alpha equals to 0.05. Is there enough evidence to reject the claim? use this p-value method. So we know that it's, the claim here again is that it's 8 miles per hour. The alternative is that it's different than 8 miles per hour. So we can calculate our Z is 1.89, and then we can find that area under the curve for 1.89. Remember, it's going to be 2 tails, right? Because of this. So it's 2 tails. So let's look that up. 1.89 right here. So 0.9706. So 0.9706. And we can subtract to get like a so we calculate that area under the curve for one of the tails, right? But because it's 2 tails, the area must be doubled, right? Because there's an area here, a p-value here, and a p-value here. So we just multiply it by 2 and we get our p-value. This p-value is greater than 0.05. So this implies not to reject this null hypothesis. So there's, because it's, we have like, how do I say it? So there's not enough evidence to reject this claim. So this is the null, because you have like significant evidence for it, essentially. And it's kind of like the reverse of the confidence intervals, is what I'll kind of say, if that helps you understand this a little bit better. But because of this, you don't reject that null hypothesis.